All right, good afternoon. So, any questions up to here? All right, cool. I'll take that as no, and everyone's doing well. Who responded so awesome? Um, well, let's continue talking about applications of number theory. So, we talked a little bit about hashing on Monday. Just a couple of other things to mention about some of this modular arithmetic. Um, one thing that relates to this is the notion of parity. So let me post some notes here. So what is parity about? Go back to older days of telecom when we communicated computer to computer using modems, and these were acoustic modems. They would send sounds, tones across the phone line. The phone company originally resisted allowing people to use telephones for anything other than talking on the phone. And when people started trying to make machines that would make tones that would be transmitted across phone lines, the phone company rebelled against that, and they threatened legal action. And the first few times these cases went to court, the courts ruled in favor of Bell Labs, and basically said, the phone company owns the phone lines and controls everything that you do with those phone lines. And if they say you can only, hold it up to your mouth and talk, and hold the other piece to your ear and listen, that's all you can do. And you weren't allowed to do anything else. And so things like fax machines and answering machines, those would be illegal, right? After a few rounds in court, eventually there was a court ruling that basically said, as long as you don't touch the copper, you can do anything you want with the phone lines. You couldn't actually go into the wall, you couldn't actually connect something that you made to the phone jack, but you could send whatever information you wanted over the phone line as sound. And so early modems used acoustic couplers to transmit sound. So yeah, early bulletin board systems, you would dial up and it would make all these cool tones and so on. And that was how communication was done. Well, that's kind of an inherently noisy system, no pun intended. Transmitting something through sound is prone to errors, right? And worst case, somebody picks up the phone while you're trying to send something with your computer, and you get all kinds of possible noise on your transmission. So this is a problem because computers are very precise, right? You're sending out binary information, and let's say you want to send the letter A, which is ASCII code 65. So in binary it looks like that, most significant bit on the left. And let's suppose that while you are sending this, you're doing this as a series of tones. So let's say it's a high tone for a 0 and a low tone for a 1. So you send high, low, high, 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 low, right? And once you're not restricted to acoustic, these might be voltage levels. So it might be 12 volts, minus 12 volts, something like that. But these are analog signals, right? And noise can come in. And so let's say there's a very loud noise at some moment, and this thing that's a high tone gets interpreted as a low tone. So this A that you tried to send might come out like that. Well, this is the ASCII code for C. So if I was entering your grades into the system, at the end of a course and I typed the letter A and the computer received what it thought was the letter C, guess what? You've got a C in the course instead of an A, right? Is that a problem? Probably. So we would like a way for the computer to know, I meant to send this and you received that, and that's erroneous. And here's a really easy way to do this. Simply count the number of ones inside the thing that I sent and add an extra character either at the beginning or the end so that the total number of ones is always odd. Okay, so this is something called odd parity. And what do? Send an extra bit. It's a 1 or a 0 so that the total number of ones is odd. So for example, if I wanted to send this number containing 2 ones, I would set a parity bit of 1. And when the computer receives this, it would say, let's see, I got 1, 2, 3 ones, that's an odd number, okay, we're good to go, no problem. But if this was what the computer received, it would say, oh, let's see, 1, 2, 3, 4, that's an even number of ones, something's wrong, and it would signal a parity error. And that parity error would cause the transmitting system to resend the information, which hopefully would come out like this, and the computer that receives it would say, yeah, that's an odd number of ones, that's good. And so you would simply, sum from I equals 0 to 7 of bit I, and reduce it modulo 2, and make sure that's equal to 1, because an odd number is always congruent to 1 mod 2. Now, as someone just pointed out in chat, what happens if you accidentally sent this, which would be a grade of G, whatever that is, maybe that's good. Your system would look and say there's 5 ones in there, that's an odd number, I guess that's okay. So it would detect single bit errors, including an error in the parity bit. If this parity bit's supposed to be a 1 and it's actually a 0, again it would say, oh, there's an even number of ones, that's a problem, right? It's not odd. So it would detect single bit errors perfectly fine, but if there were 2 errors, it wouldn't notice. And so you can do more complex versions of this, where you do things like take a weighted sum of these bits, and you multiply them by different things, and you add them together, and you reduce modulo something fancier than 2. And this is how you get to things like, hash codes, MDA and SHA and so on. So that's a really early application. And we still do things like this. So early memories that you could buy for a computer would have parity bits to detect if one of the bits in the memory had gotten flipped. But double flips, hard to do anything about. So slightly more expensive memory was called ECC. That was error checking and correcting. That used 3 bits for every 32 bits that were stored, I believe. And it could detect, I think, 2 bit flips, and it could correct a single bit flip. So there's enough information that if 1 bit got flipped, this code could actually correct it. Parity, if we get this by mistake, right, go back to the 0 case. If we get this, we know there's a problem, we have no way of knowing where that problem is. Okay, but with ECC you could actually correct single bit errors. And there's lots of good number theory that goes into all of that. The other thing I want to mention, and it's similar to that, is the general notion of check digits. And so let me find something. This will work. So here's a box of incense from the corner store. There's a barcode which is used to scan the item and figure out what it costs. And if we zoom in on that barcode, let's write down what this is. So it's 43006 01133, and I've got a 7 over here and I've got a 6 over here. All right. So so this gets scanned and looked up in a database, and from there it can figure out what the item is and what the price is. All right. So so what is this code? It's a 12-digit code. The first digit here, the 6, that's a product class. It's a single digit, so it's pretty coarse-grained, but it basically says what kind of item is this? Food, you know, etc. These 5 digits are the manufacturer, and these 5 digits specify the product itself. And for each manufacturer, there's different product codes. So that's presumably the unique code for this particular manufacturer for this particular type of incense. This last digit, this is a check digit. And the purpose of the check digit is to help you know if there's an error in these earlier digits. Now, there's the human readable code that we can read, you know, these digits, but optical character recognition, traditionally kind of a tricky area for machines, and so there's this barcode which is read by the scanner, much less error prone. Nonetheless, it can still be tripped up. It's still possible that, you know, there might be a smudge here, or maybe someone might even come in maliciously and try to change one of these bars to change, you know, the barcode for a 54-inch TV set into the barcode for a bottle of water, in the hopes that, you know, they can buy their TV for a few dollars. All right, so there's a check digit, and the check digit is there to help you know whether this combination of digits that you see here is correct or not. And so it's kind of like a parity, but it's a little bit fancier. All right, so let me write this down on a fresh sheet of paper. And I'll admit, normally when I do this, I figure this out ahead of time and make sure it works. I haven't done this before because I just grabbed the first thing I could find. So we'll see if this works or if I embarrass myself by not knowing how to do UPCs. But here's the basic idea. We've got 11 digits and we've got a check digit. Okay, we're going to take a weighted sum. So I'm going to call these X1, X2, X3, X11, X12. Okay, I'm going to do the following calculation. 3 times X1 plus X2 plus 3X3 plus X4 all the way up to 3 times X11. So I'm going to add up these first 11 digits, but I'm going to take the odd positioned ones and multiply by 3. And then at the end, I'm going to reduce that modulo 10. And then, if I end up with something which is not 0, I'm going to do 10 minus that weighted sum. And that should be my check digit. Alright, so I don't think I need a calculator, but let's try this. So, 3 times 6 plus 4 plus 3 times 3 plus 0 plus 3 times 0 plus 6 plus 3 times 0 plus 1 plus 3 times 1 plus 3 plus 3 times 3. So 18 plus 4 plus 9 plus, I'll skip the zeros, 6 plus 1 plus 3 plus 3 plus 9, and I want to reduce this modulo 10. So all I need to do is keep the ones digit as I do my addition. So 18 and 4 is 22, that's 2 and 9 is 11, 1 and 6 is 7, plus 1 is 8, plus 3 is 11, plus 3 is 4, plus 9 is 13. Right, reduced modulo 10, that's not equal to 0, so I'm going to do 10 minus 3, and that gives me my 7, and that needs to be the check digit for this to be a valid UP code, and it is. Right? Now, if any of these digits had changed, then I would not have calculated a check digit of 7, and I would have said something's invalid here. And if the check digit got changed, I would have calculated the check digit should be 7 and it doesn't match, something's invalid here. And then the scanning machine beeps and the person picks it up and types the code in by hand. Alright, and this is guaranteed to pick up any single digit error, right? So if any of these digits change, it will notice. And 90% of all possible transpositions. So a common error when you're keying in codes like this is to swap two things, to type a 3-4 instead of a 4-3. Well, 90% of such transpositions this code will catch. And it's because digits that are next to each other are weighted differently. And there's a 1 in 10 chance that you might transpose two digits and not notice that you'll end up with the same code. So this is a pretty solid code, right? And it's just based on some of these principles of modular arithmetic that we've been talking about. Okay, another example is ISBN codes. If you look at the back of any published material, a book, etc., there's that barcode on the back. It's labeled ISBN. There's different versions of ISBN, but the same thing. It's basically a weighted sum of the digits that's reduced modulo something, mod 11 in this case, to give you a check digit. And it lets you know if that rest of the code is valid and detect if there's errors. Alright, so various applications of number theory related to integrity checking, basically. And so that's useful. Alright, so let's talk about crypto systems. So cryptography, what's the basic idea? Fundamental premise of any kind of information security is the following. Physical security does not exist. Okay? You can't expect to physically keep somebody from having access to something. Whether you're locking something in a vault or burying it in the ground or giving it to somebody who carries a big sword, you cannot guarantee physical security. Right? There might be 5 people with bigger swords who will eventually get that piece of paper. Or there might be someone with a big bulldozer that will break through your concrete bunker and get to, you know, the Krabby Patty recipe in the bottle, right? So physical security is not the way to secure information. So cryptography is built around the idea that assume the person is going to get access to the information, but try to make it so that information is not usable by somebody who's not authorized. All right? So we're assuming people have access to the information, but we want to keep them from being able to make use of it. So we jumble it up in some way so that if this person's not authorized, they can look at, you know, the physical thing containing the information, but they don't know how to interpret it. So cryptography is sort of about, you know, jumbling things up, making it look so that it's something that's not meaningful when in fact there is meaning there. All right. So what are some examples of this? Really early example, a Caesar cipher. Okay, so a Caesar cipher is basically a mapping from the set of letters, say, to the set of letters. And an easy way to do this is maybe a shift cipher. So let's code our letters. Let's just say A equals 1, B equals 2, C equals 3, and Z equals 26. Hold on 1 second. I've had a fruit fly in here for 3 days after non-existent bananas. So I think I just got it outside. All right, so we have coding of letters A through Z, 1 through 26. Here's a really simple example of a shift cipher. F of n equals n plus 5 mod 26. I guess I should probably start from 0 to make modular stuff work well. All right, so well, the bananas used to exist, but they turned into banana bread, and now the banana bread is gone, but the fruit fly remained. There's a poem in there somewhere. So A is 0, B is 1, Z is 25. We can take a letter n, one of these numbers, add 5, reduce it modulo 26. It will give us a new number. All right. So f of the character A will be 1 plus 5 is 6. That'll be the letter F. F of B will be the letter G. F of Y, well, Y is letter 24, will be 24 plus 5 equals 29, which is congruent to 3 mod 26, which will be the letter D. All right, so this function takes letters and turns them into other letters. And so we can take a message like happy, and by applying this function, we can transform each of the letters. So this will become an M, this will become an F, P will become a U, and Y will become a D. And so there's what our message translates into. All right, and this is, you know, the decoder ring you used to get in the box of cereal. You can make this with a pair of dials where you move one relative to another. There's my fruit fly. It came back in. You have a pair of dials where one moves relative to the other, and it basically does addition or subtraction. And we could add or subtract either way. And so that's an early cipher, and it's credited to Caesar, right, to write messages this way. And then if somebody doesn't know how the cipher works, right, they see this and they have no idea what the secret message is. All right, some obvious problems with this. Okay, the first problem is it's a pretty simple cipher, right? If you know that the person is just adding something to the letters, there's only 26 possible encryption keys, right? You could be shifting by 1, 2, 3, 25, or maybe by nothing, which would be a silly cipher, and you could just try all of them, right? And eventually find, you know, a word that you recognize, and that's probably your key. Alright, someone in chat just posted a cipher they used to use in middle school. So yeah, using different symbols instead of letters, and then rules for swapping letters, doubling certain letters, and so on. That's pretty cool. Ciphers are fun. It's fun to try to come up with stuff, and it's also fun to try to crack stuff. And you know, you can earn a living at this, right? There's agencies, or maybe no such agencies, of the government that, you know, hire people to work with this stuff. And it's a fascinating area. I mean, this stuff has been around for thousands of years, literally. And it's a continuously growing and evolving area. So shift cipher is really easy, right? Because there's only a certain number of codes, so that's one problem. Second problem is that, the letter A always maps to the same thing. The letter P always maps to the same thing. And even if I use different shifts for different sets of letters, maybe vowels would shift one way and consonants would shift another way, there's a problem, which is you can do a frequency analysis attack pretty easily. So if you look at most written languages, you can find how frequently different symbols occur in typical text. Right? For example, in English, the letter E is the most common letter. And you can make a table of frequencies for how often different letters occur in typical text. All right? So now if you have a whole bunch of text that's been encrypted using someone's encryption system, and you know that the letter E always maps to the same symbol, just find the symbol that occurs the most. That's probably the letter E. And you can do this for the first few most frequent or the least frequent characters, right? And if you know, for example, what a Q maps to, you can probably figure out what a U maps to, because most English words, Q is followed by the letter U. The letter B will be followed by certain things. It will not be followed by certain other things. The letter E is preceded by certain things. It's not preceded by certain other things. So if you know the structure of the language of the material that you're translating, you can start to attack it by just looking at frequencies. So that's another problem. And yeah, this all gets into good Wheel of Fortune stuff. There's a bigger problem with this. And this is going to lead us into RSA. The biggest problem with this is that in order to encrypt my message, I need to know what the encryption key is. So the encryption key is 5. So if I want somebody to be able to send me a secure message, I should tell them, yeah, my encryption key is 5. That's the key I always use. It's my password. And now if somebody wants to send me a message, they can shift everything by 5. Here's the problem. Somebody else also sends me a message using the same encryption key. This person who knows my key is 5, they can decrypt that other message. If all my secret messages are coming to me shifted by 5, anybody who knows how to encrypt, shifting by 5, knows how to decrypt. Right? So this is a characteristic of what's called a symmetric cipher. Symmetric ciphers have the property that the same thing that lets you encrypt a message lets you decrypt it. Okay? Encrypting is going from plain text to ciphertext. Decrypting is going from ciphertext to plain text. And those are symmetric processes with a shift cipher. When I get your message, I'm going to subtract 5 to get back to the original. But anybody who knows that I'm having people add 5 to crypt their text knows how to decrypt messages. So imagine that we were trying to do online commerce. Okay? So Amazon tells my browser, go ahead and add 5 to your messages when you want to send me your credit card number. So I'm going to add 5 to each digit. Well, the person in the parking lot who's picking up my Wi-Fi, they see a credit card number going through. They know that 5 has been added to each digit. They subtract 5, they got my credit card. Okay? So e-commerce, right? Being able to send secure information over insecure channels like Wi-Fi or pretty much anything would not be possible with a symmetric key. Unless, Amazon could tell me, hey, okay, your password is 5, and they could tell you your password is 17, and they could tell someone else your password is -6, right? And then I could see the message that you're sending, but I wouldn't know that your password was -6, so I wouldn't know to add 6 to get your credit card number. But that's not feasible, right? There's no way that you can expect a central agency, a credit card company, Amazon, PayPal, whatever, to give each person their own password. So necessarily, with a symmetric cipher like a shift cipher, if I am encrypting something, Anybody else who knows how to encrypt can also decrypt. And that's the end of the security. Because again, you cannot assume that the information I send is secure. Okay, you have to assume that as soon as you send it out, everybody in the world has access to it. And that's a pretty valid assumption, right? Well, anybody who has network access can access it. Because wireless signals, I mean, those are in the airwaves. All you need is a receiver. All you need is a router, right? You can put your router into monitor mode and pick up packets that are being transmitted, even if they're not being sent directly to you. So this makes stuff kind of inherently insecure. All right, so one more example of a symmetric cipher would be a permutation cipher. And this one avoids some of these difficulties. So how does a permutation cipher work? Or a transposition cipher? So we define permutation, let's say from the digits 1, 2, 3 to the digits 1, 2, 3. And let's say sigma of 1 is 3, and sigma of 2 is 1, and sigma of 3 is 2. Okay, so now here's my message. And I'll put a blank at the end because I want a multiple of 3 characters. And I break my text into groups of 3 characters. And I use this transposition to say, okay, the first character of my ciphertext should be whatever the third character of my plain text was. So I take the P, that becomes my first character. The second character should be the first, that's an H. And the third character should be the second, that's an A. And for my next block, I do the same thing. The first character will be the third, so that's a space. The second character will be the first, that's a P, and the third character will be a second, that's a Y. And so my original message, happy, gets changed into PHA space PY. Now, a frequency analysis won't necessarily help here with single letters, but I can do an analysis on combinations of letters, ST, TH, QU, and see how many times certain pairs of letters appear. And if this is a big enough block size, which it would be if this was a complex permutation, I can start to find patterns inside each block and do some reverse engineering based on that. The other problem with this, though, is it's still symmetric, right? If I'm going to encode something like this, the person who's going to decode it simply has to do the reverse. They take the third character, that becomes the first character becomes the second becomes the third. But if you know how to encode, you also know how to decode. So that's another symmetric cipher. And again, it doesn't work for things like e-commerce. All right, so we need something more interesting than that. So we need an asymmetric cipher. This is the idea of a cipher where we have one key for encrypting and a different key for decrypting. So you can tell somebody how to code up a message to send to you, but the way you decode it is different. And the key that you use for coding does not let you decode, and, this is important, it does not let you figure out the key to decode. And if you have that kind of setup where you have one way to code and another way to decode, and knowing how to code doesn't tell you how to decode, you can do e-commerce. Because now Amazon can tell everybody, hey, here's what you use to send me secret messages. And you can tell everybody what that code is for coding their messages, and nobody can figure out the decode key for reading those messages back. So you keep that as a secret. So we have a key pair. We have a public key and a private key. Okay, and this is what we do with like RSA, for example. And we do this with Git. If you're in 224 or you know Git, you make a public-private key pair. And the public key, you can give that to everybody. People can use it to send you encrypted emails. You keep the private key to yourself and you use that to decode the emails. So PGP and GPG and things like that, these are all asymmetric ciphers that you can use to do things like, have people encrypt emails to you without having to give them the decryption capability. And so yeah, so comment in chat here about backdoors and the danger of encryption and so on. This is a really interesting area, right? I don't know if it's still true, but certainly in the 80s, encryption algorithms were classified as munitions, as weapons, right? And they were controlled by the government. Encryption is a scary thing to a lot of government agencies because it means that people who are communicating with one another and planning to do bad things, right, whatever that might mean to you, can do it in secret, and eavesdropping becomes difficult. All right, so this is a good point to launch into story time. So I want to talk about these people. All right, so this is a classic picture. Yeah, story time is fun, right? All right, so this is Ralph Merkle, Martin Hellman, and Whitfield Diffie. Okay, Ralph Merkle I've actually met. I met him when he was doing nanotechnology in the early 90s. Put together a company called Zyvex, and he came up to Mathematical Sciences Research Institute in Berkeley, California, and I was a student there. And he gave a talk on nanotech, so he's a really interesting character. Martin Hellman, this person in the middle, he was working at Stanford. Okay, and he was interested in this idea of an asymmetric cipher. He was interested in a way of being able to code information that would not necessarily tell you how to decode it. And he had this idea, and he started talking to some of his colleagues about it, and the general consensus from everybody he talked to was that's impossible, right? Because all we'd ever thought of was shift ciphers and Caesar ciphers and, decoder ring ciphers and things like that, where encrypting and decrypting are basically the same thing, right? And if you know how to do one, you know how to do the other. Yeah, that is Hellman, like Diffie-Hellman. Exactly. But he wanted to develop this idea anyway, and he was thinking ahead, actually, among other things, to electronic commerce. Okay, so this was in the 60s, all right. Early days of computers, but people were thinking about this stuff anyway. Science fiction at the time, right? So Diffie had a bachelor's in mathematics from MIT. He got his BS in 1965, and he was traveling around the country, and he was talking to crypto researchers and asking interesting questions about how cryptography is done and how it could be done. And he got to IBM at one point, and some IBM people told him, hey, there's this guy named Hellman. You should talk to him. Right? He's out at Stanford. You might have some things in common. So Diffie went to Stanford, and he made an appointment, and it was a 30-minute appointment. So he knocked on his door in the middle of the day. He introduced himself. They started talking. They talked, and they talked, and they talked. And it got to be dinner time, and they had dinner together, and they talked, and they talked. And he left about 11 p.m. that night. Spent the whole day there chatting with this person. So kindred souls, right? So they were kicking around ideas and started doing some collaboration. All right, Ralph Merkle around this time, he was an undergrad at Berkeley, and he was taking a course in computer security. And they had to come up with a project to do for the quarter, okay? And he came up with this idea of doing some kind of crypto system like this. And he proposed it to his teacher, and the teacher responded on the proposal saying that your project is muddled terribly. Okay, that was the quote I got, muddled terribly. And so Ralph Merkle responded, like all good undergraduates would, by dropping the class so that he had time to work on this on his own. So he started working on this project on his own time, trying to come up with a cool crypto system. So he did that. He finished his undergrad at Berkeley. He went on to work on a master's also at Berkeley. And around the same time, 76, he was talking to some people, kicking around his ideas, and somebody made the comment to him, you know, there's some guys up at Stanford who talk just like you do, and you should go talk to them. So he went up to, down to Stanford and introduced himself to these people and started talking. And so anyway, he became Hellman's doctoral student, and he started working on his PhD under Hellman. So that's how these three came together, okay? So go forward about 10 years, 1976, and these people have figured out a public key crypto system, an asymmetric cipher. Let's see, some people are getting echoes. I'm going to mute everybody, just in case of that. All right, so 1976, they figured out an asymmetric cipher. They decide to publish it, right? Because that's what you do in research. You come up with an idea, you put it in a paper, you publish it. And then your peers can look at it, they can try to reproduce your results, and they can either verify your results or say, hey, I got a different result. This is what we do in labs. This is my lecture from Engineering 250, 270, right? Why do we write lab reports? It's about peer review. So they put this paper together, and some of their colleagues got worried and realized that, like, if this information was made public, then so-called bad agents could, you know, make plans to do bad things in secret, and the government might not be able to spy on them anymore. So some of these colleagues contacted the NSA. That's the National Security Agency, also known as no such agency. They contacted NSA, and NSA started looking at this work that they were doing, and they classified it as a munition, okay, basically an instrument of war. And they came to Hellman and they said, you know, we know you're planning to present this at a conference next year. If you do that, you're going to be arrested and charged. All right. So there was a conference October 77, and this was a showdown. Government basically said, this is classified, this is national security, you're not allowed to talk about it to anybody. If you do, you're going to be arrested, thrown in jail. All right, so what do you do in that situation? Well, Hellman talked to Stanford, and Stanford basically said, if you're prosecuted, we'll help with your defense. We'll pay for your attorney, we'll be there in court with you, and so on and so forth. If you're convicted and found guilty, we cannot pay your fine, and obviously we cannot go to jail in your place. So we'll help you with your defense, but, you know, if it doesn't work out well, it's going to be your burden. And he wanted to do the conference anyway. But he advised his two students not to go on stage and present this material. Because the students, they were, you know, early, and so you know, this person, he was a tenured professor, he had, you know, a good reputation, he had a solid footing to stand on. His students were early in their career, didn't have a lot of savings, and so on and so forth. His students both at first decided, you know, to heck with that, we want to present this is our research too. Talked to their families and eventually agreed to sort of stand down. So Hellman did the presentation. The grad students were sitting on the side. The government was in the back of the auditorium. And in the end, nothing happened. They let them do the presentation, and as soon as they presented this, that was it. The genie was out of the bottle, right? Because now everybody in the audience knew, you know, how to do this crypto system, and that's it. There's no more secrecy around it. So that was a interesting showdown, and it wasn't the end of things. So I don't know how many people here ever used Netscape. Let's go back into the good old days of the 80s. Netscape was an early browser, right, before Firefox came along. And there were two versions of Netscape you could download. There was a a strong encryption and a weak encryption one. And if you were in the US, you could download the strong encryption version as long as you agreed not to use it outside the US, not to give it to anyone outside the US, etc. Otherwise, you had to download the weak encryption one, which was like 48 bits or something like that. So people were really like, you know, concerned about crypto systems and whether people would have access to this information and to this software, right? Now today, if there's an algorithm out there, you know, a 12-year-old on any country in the world will pop up and be able to code this in Python and put it out on the web, right? So that's a done deal. But in the 80s, you know, there was this kind of belief, I guess, that, you know, only a few very, very large companies had the expertise to actually write code to implement one of these advanced encryption systems. I don't know what the thinking was. But now, you know, it's totally clear that you cannot protect algorithms. Okay, just like you can't protect physical information, you cannot protect algorithms. You cannot rely on an encryption system based on nobody knows how I'm doing the encryption, right? Because people will reverse engineer code, and if you make executable code, you can reverse engineer it. You can't see the original source code, but you can figure out the algorithm by running it through a debugger, or worst case, by looking at the ones and zeros, getting a table of opcodes, and just writing out the assembly language yourself. So algorithm security does not exist. What's cool about RSA and other things like this is that even if you know the algorithm, you still can't defeat it, theoretically. Now this doesn't always happen, okay? So WEP, you know, was one of the ways that you could encrypt your password on early routers. Well, that turned out to be crackable in a few minutes, right? So people find problems with these algorithms that make them crackable, or the underlying technology gets good enough that something which seemed impossible to crack, you know, 20 years ago is doable in a few minutes now, right? So yeah, MD5, for example. You know, 64-bit encryption used to be like, oh, it'll take, you know, 1 billion computers 1 billion years to crack this, and now, you know, it's a few minutes on a 3 gigahertz CPU. Or, you know, you get some time on AWS and run a distributed algorithm and stuff like that. We're not even going to talk about quantum computing, which kind of blows all the stuff out of the water. But RSA has held up. It seems to still be a pretty good way to do public key encryption so far. But yeah, when quantum computing finally breaks, all this stuff is done. And then you're back to like the sneaker storyline, right? Where there's like no more secrets. Yeah, so someone mentioned 128-bit used to seem like plenty. Quantum cybersecurity, yeah, fascinating area, about which I know almost nothing, except what I read. All right, so let's talk about RSA in some detail. And let's see. I never remember what the names are, but I have them written down. So this is Ronald Rivest, Shamir, and Adelman. So there's your RSA. And an excellent quote in chat right now. If you think you understand quantum mechanics, then you don't understand quantum mechanics. Which is probably true. Along with the key to understanding recursion is understanding recursion. That's the one we'll talk about in CSE222. All right, so RSA, public key crypto systems. So the security of RSA is based around basically the following idea. If you have two very large prime numbers, multiplying those numbers, very easy to do. If you take the product of two prime numbers, factoring it into the two original primes, very difficult to do. All right, so you can take two large primes, and even if they're like 1,000 digits each, to multiply those two numbers together, not a problem. Okay, it's trivial to write a program, well, relatively trivial to write a program in C or Python or Java that would do pencil and paper add and shift multiplication and take 2,000 digit numbers and give you the product. And you know, our favorite go-to calculator, BC, you know, we'll do large multiplication. These aren't 1,000 digits, but they're, you know, a bunch. Not a problem at all. But if I give you this number and I say factor that for me into two integers whose product is equal to this, that's a hard thing to do in general. All right, so RSA is more or less based on this idea that multiplication of two numbers is pretty easy. Factoring a product into the two numbers that gave you that product can be very difficult. And it's most difficult if the two numbers you multiply are prime, because then the only way to factor this product is as those two particular primes. And so we build RSA on top of pairs of prime numbers. And we want large primes. So a good algorithm today, several hundred digits for each prime. So prime numbers with several hundred digits. We can calculate these, but they take some work. All right. So how does RSA work? So we're going to start off with a pair of primes, P and Q. These are large primes. And we're going to go through this. We've touched on everything that we need to do RSA. What I want to do here is basically show you the algorithm and show you a kind of hand-wavy argument that it actually works, that we can encrypt and decrypt using this algorithm. And then either on Friday, or maybe I'll just make a video of it, we'll go through actually encoding something using RSA and decoding it by hand, just to sort of see the process. I'm not going to ask you to reproduce any of this on an exam. I may ask you about, you know, the difference between a symmetric and an asymmetric cipher. I may ask you, you know, what's the fundamental difference between RSA and a Caesar cipher, or something like that. But I'm not going to ask you to do the stuff that we're about to do. Okay, so this is just kind of sit back and enjoy and think about and ask questions if you like, but don't stress over it, because this is goofy. Okay, this is the stuff that, you know, people said was impossible not too long ago. All right, so P and Q are two large primes. N is their product. All right, that's pretty easy. E is a large number, relatively prime, to the following product, P minus 1 times Q minus 1. So the greatest common divisor of E and P minus 1 times Q minus 1 is 1. Right, relatively prime, no common factors. So if you find your primes, you can find their product. You pick some large number that's relatively prime. How do you do that? Well, you know, take P minus 1, Q minus 1, write those as products of primes, and then just pick, you know, a product of primes and powers of primes that don't come from this list. And you'll end up with something that has no common factors to P minus 1, Q minus 1. All right, so the encryption key is a pair of integers. It's the integer n and it's the integer e. So that's the key that you would publish. And you would tell people, when you want to encrypt a message to me, here's the pair of integers that you use. All right, that's your public key. All right, so we need to talk about how you use this to encrypt a message, and then we need to talk about how do you decrypt the message. Okay, so this is generating the key. All right, so let's talk about how we use this encryption key. So we need to take our message and we need to turn it into a bunch of numbers. Okay, and I'm going to use a simplified alphabet here. So we're going to stick with what we started with for a Caesar cipher. A is going to be 0, 0, B is going to be 1, C is 0, 2, Z is 25. But I'm going to insist that these are 2-digit numbers. So, 2 will be a 0, 2. All right. And then we're going to take our message, and, let's say our message is happy. And we're going to break it into blocks. Well, first we're going to replace each letter by its code. So this is going to be 0, 8, 0, 7, 0, 0, 1, 5, 1, 5, 2, 4. All right, and however much text you have that many times 2 digits. Okay, and this looks like a big long integer. Okay, now we're going to break it into blocks. And the block size is really critical. So, convert each letter to a number. And in practice, we'd have more than just 26 letters. We'd have lowercase, uppercase, punctuation. So you could use ASCII codes or something like that. You might use 3-digit numbers. This is a simplified version of it, okay? So somehow convert each letter to a number and write those numbers out. Okay, next we're going to break our text into blocks. Okay, what we want is we want a large N. So we find an N such that the following is true. Let me call this big N. Right. We want a large value of n such that if we write n 25s next to each other, that's smaller than this first part of the encryption key n. Okay? That's not as weird as it sounds. What we want to do is we want to basically break this message up into fixed size blocks so that we know that if we look at all of the letters in one of these blocks, it's a number smaller than n. Right? The largest this could be was if we encoded a bunch of z's, it would be 25, 25, 25, 25. So we pick an n so that if we have that many 25s, it's still smaller than n. But if we added one more 25 here, it would be bigger. So we're breaking it into a block size such that, regardless of the letters, this number will be smaller than n. Okay, our encryption key. And that's because we're going to do a lot of work modulo n, and when we're done, we're going to come up with something modulo n, and if we know that our original message was smaller than this, then we know that it will be, whatever our number is congruent to mod n. So that's just kind of a simplifying assumption, or what we call in technical terms a nicety nice. Okay, so let's suppose that m is our message, so we encrypt one block at a time. Now remember, if these are 700-digit primes, then their product's going to be, several hundred digits. So we're going to have several hundred characters in one block. So we take that whole chunk of letters, that's one block, we're going to encrypt that. And then we're going to take the next block, encrypt that, next block, encrypt that, and so on. So we're just going to talk about encrypting a single block now. Okay, and the understanding is that whatever we turn that block of characters into is going to be smaller than n. Okay, so how do we encrypt? It's very easy. So let M be your message. For example, this thing up here. Your ciphertext, that's your encrypted message C, is just M to the E modulo N. Alright, so your encryption key is N and E. You have a message you want to send, you basically break it up into a bunch of numbers, right, by doing that replacement. You take the message, raise it to the power E, reduce it modulo N, that's your ciphertext. Alright, very straightforward to do, a lot of work, but straightforward. Because we know about modular exponentiation, for example, we can raise things to powers pretty efficiently. If this was 1500 bits, we only need to calculate 1500 powers of M, and then multiply them together in whatever way gives us this exponent E. So this, for a computer, trivial to do. Alright, and it gives us our ciphertext. Alright, now how do we go from our ciphertext back to M? How do we decrypt? So I'm going to give you an algorithm for doing that. That'll probably be the rest of this class. And I'll convince you that when we apply this decryption algorithm, we end up with M. Okay? What I'm not going to convince you is that it's very hard to know how to decrypt unless you know the specific decryption key. People way smarter than myself have figured out, you know, good reasons why it's very difficult to get the decryption key from the encryption key. And have also figured out, presumably, that there's no way to decrypt unless you know the decryption key, other than brute force, so no efficient way to decrypt. But we're not going to do that, okay? We're just going to figure out how we decrypt this once we know the decryption key. Alright, so decryption. Alright, so hold on tight here. So assuming that you're the person who came up with the original key, that means you know those original primes, P and Q. Right? The public knows their product, N, because that's part of the public key. But presumably knowing that does not tell you P and Q. But since I'm the one who's creating this public-private key, I know what the primes P and Q are that I use to get N. Okay? That's the essential part for coming up with a decryption key. Alright, and this is all good fun now. So, if you know P and Q, then you can find a number D such that D times E is congruent to 1 modulo P minus 1 times Q minus 1. Okay, why is that? Because remember, when you picked E, we picked something relatively prime to P minus 1, Q minus 1. So the greatest common divisor of E and P minus 1, Q minus 1 is 1. Well, I mentioned without proof, but there's an algorithm we can use to demonstrate this, that if we know the GCD of two things is that, it means we can find something times the first plus something times the second, which is equal to that GCD. Well, this means there's something we can multiply E by, which makes it one more than a multiple of P minus 1 times Q minus 1. I might need to throw a minus sign in here. You can negate this. You can also make this equal to minus 1. So yeah, okay, so if you can do this, you can negate your constants. You can make this equal to minus 1. And then if I just switch my terms around, b times p minus 1 times q minus 1 plus 1 equals a times e. So a times e is a multiple of p minus 1, q minus 1 plus 1. It's one more than this. And so that number a, that gives me this equation, that would be my value for d. All right, so you can find this d if you know the original primes, because then you know what p minus 1, q minus 1 are. All right, so d is your decryption key. And the claim is that if you take your ciphertext and you raise it to the d, that will be congruent to your original message modulo p times q. So mechanically, what's the rehash? Start with two large primes, multiply them to get an n, find an e that's relatively prime. There's your public encryption key. To encrypt your message, take your plain text, raise it to the e modulo n. That gives you your ciphertext. Meanwhile, when I came up with these primes p and q, I also remembered what my decryption value was, d. When I want to decrypt the ciphertext, just raise it to the d, reduce it modulo n, that gives me my plain text back. But if all you know is n and e, the claim is it's almost impossible to figure out d. But if you can factor n, you can find p and q. Now you can find a decryption key by just finding something that multiplied by e is congruent to 1 mod that. So the security is based on the difficulty of factoring. All right, so we have, oh, we got time. Our class technically goes till 1:55, so we got time. Let's see at least a demonstration as to why raising your ciphertext to the D will get us back to our original message. All right, so this is going to be a lot of stuff that we've been doing, kind of all thrown together. All right, so D times E is congruent to 1 modulo P minus 1 Q minus 1. That's how we found our D. Okay, that's how we chose it. So there exists some constant K such that D times E equals 1 plus some constant times P minus 1 times Q minus 1. So if I take my ciphertext and I raise it to the D, well, what's my ciphertext? My ciphertext was M raised to the E. So C to the D is going to be the same as M raised to the E raised to the D. Right? And this is mod N. Right? So this is going to be the same as M raised to the D times E, because that's the law of exponents, which is going to be the same as M raised to the, well, I'm going to put this in place of D times E, 1 plus K times P minus 1 times Q minus 1. All right, and this is all mod N. All right. Well, n is p times q. And if something is a multiple of p times q, it's also a multiple of p. And it's also a multiple of q. That's kind of like a homework question that you did, right, with divisibility. So by the definitions of divisibility, this tells us that c to the d is also congruent to m to the 1 plus k times p minus 1 times q minus 1 mod p. And c to the d is also congruent to m to the 1 plus k times p minus 1 times q minus 1 mod q. All right. So simplifying assumption, let's assume relative primeness between m and p, as well as m and q. In other words, let's assume that your message is not a multiple of p or q. And that's almost always going to be the case automatically, because what are the chances that you would take a message, rewrite it, you know, with numbers 0 through 25, and you end up with a multiple of this 700-digit prime? It's really unlikely to happen. If it does, I don't know, add an extra space to the end, or add a space in the beginning, or you know, put a period at the end or something like that. So you can tweak your message. So we can assume that this is the case, and we'll modify the message if it's not before we encrypt it. All right. So well, we can't before we encrypt it. Let's just assume that's the case. Okay. So the GCD of m and p is 1. All right. So Fermat's little theorem, remember that, tells us the following. It says m to the p minus 1 will be congruent to 1 modulo p. And also m to the q minus 1 will be congruent to 1 modulo q. Right? And the only time FLT doesn't apply is if m is a multiple of p, because p is a prime. And that's almost never going to happen. So we know that if we take this really long message, right, several hundred digits, and raise it to the p minus 1, it's 1 more than a multiple of p. That's Fermat's little theorem. That's how we cut through all of the iterations we might have to do this calculation of c to the d, and we reduce it to something simple. All right, so let's figure out what c to the d is now. So c to the d is m raised to all of this stuff, right? Which I can break this exponent up. This will be m to the first times m to the k times p minus 1 times q minus 1, which will just be m times m to the k times p minus 1 times q minus 1. And I'm working right now mod p. Well, let's take this and let's break this up into pieces. This is m to the p minus 1 raised to the k times q minus 1. Law of exponents. Well, m to the p minus 1 is congruent to 1 mod p, so this is m times 1 raised to the k times q minus 1. And 1 raised to anything is just 1, so this is congruent to m. So our ciphertext raised to the d is congruent to m mod p. All right. I can start working on the back now. So c to the d is congruent to m mod p by doing the same argument with q instead of p, c to the m will be congruent to m mod q. Here comes the last piece. This is the Chinese remainder theorem. Since these moduli are relatively prime to each other, because they're in fact both prime, there exists a solution to this pair of simultaneous equations. So there exists a unique C, a unique solution to x to the d is congruent to m, x to the d is congruent to m, right? And we know that C satisfies both of these equations. So so if you plug this through the Chinese remainder theorem, which we talked about but we didn't prove, what you'll find out is that C to the D is actually congruent to M modulo P times Q, which is modulo N. So you take your ciphertext, you raise it to the D, you reduce it modulo N, you're going to get a number smaller than N, which is congruent to your original message. Well, your original message was also smaller than N, because we picked a block size so that the message would always be less than N. And so C to the D will actually be equal to your original message if you reduce it modulo PQ. And there you go, you've got your original message back. So, so I did this the other night. I took a message happy and I started encrypting it up. And for my large primes, I picked 37 and 101. So this is an example. We don't have time to go for this because class ends in 3 minutes. But I may throw this on a video. Anyway, it took 4 pages to do the encryption and decryption. Basically, I took primes 37 and 101, did a block size of 2 letters, came up with a decryption key of 3287 to go along with the encryption key 3737, 23. That's the product of my primes and a number that's relatively prime to p minus 1, q minus 1. And so I took my message 801 and encrypted it using this key, and basically went through the modular exponentiation by hand and came up with a ciphertext of 1589. And then, knowing the original primes, I came up with a decryption key based on the requirement that 23 times d should be congruent to 1 mod 3600, that's p minus 1, q minus 1. And I did that by using Euclid's algorithm and basically solving the equation to find something times 23 plus something times 3600 is equal to 1, and that led me to a decryption key of 3287. And I mean, you know, these are small primes, that's half a page of work basically to do that. And then I tried to take my ciphertext, which was 1589, and theoretically if I raise it to this power, I should end up with my original message. And so I did that using modular exponentiation. So here's my number to that power, and I need to reduce it mod n 3737, and found 14 powers of 1589 in that moduli, and came up with these numbers, wrote my exponent in binary, and then multiplied the appropriate powers together, still reducing modulo 3737, and came up with my original message 801. And I did this with a pocket calculator, right? Because modular exponentiation, we don't have to deal with terribly big numbers. So I don't want to spend class time doing that, so I think I will actually just throw together a short video sometime in the next day or two and show you how I did this, just as an example of taking specific primes and a specific message, crypting it, and then decrypting it, and seeing how that works. But anyway, that's the basic story of RSA. A pretty fast run through of something that could be, you know, a several week succession of lectures. But anyway, just to give you an idea of it. And it's cool because it uses, you know, a lot of the stuff we've been doing: GCD, Euclid's algorithm, Chinese remainder theorem, Fermat's Little theorem, modular exponentiation, properties of modular arithmetic, and so on. And it all kind of comes together in this beautiful application. All right, so that's pretty much it for our number theory section. Friday, I want to start talking about mathematical induction. So we're going to go back to working on proofs, and this is going to be sort of the biggest takeaway from this course will be mathematical induction. It's the real driver for this course, and it's the thing that's going to play right into CSE215. All the algorithms we do in there that are recursive will basically just be a computer version of mathematical induction. So we'll start something totally new on Friday, which is mathematical induction. I will see you then. Have a great afternoon. Thanks.